A tank holds 10,000 kilograms of a saturated solution of sodium carbonate at 30 degrees Celsius. You want to crystallize from this solution 3,000 kilograms of sodium carbonate decahydrate without any accompanying water. The solubility data of sodium carbonate as a function of the temperature is shown below. So the first question is, to what temperature must the solution be cooled? So the first thing we have to do is to draw a block diagram. On the left side of the block diagram, we must list all the components entering the crystallizer. That includes the feed of 10,000 kg, the solubility of 38.8 sodium carbonate per 100 grams of water, and the mass fraction that we should still solve later on. On the right side of the block diagram, the mother liquor or the product, we should list all the components that is coming out of the crystallizer, and that includes the saturated solution at temperature unknown and the mass fraction unknown. Below the crystallizer is listed as the crystals, which we have 3,000 kilograms. So the first step in solving the problem is we get the mass fraction of the saturated solution at the feed. So the formula of mass fraction is mass of solute over mass of solution. So first, we must get the mass fraction of sodium carbonate at the feed. So given 38.8 grams per sodium carbonate over 38.8 grams of sodium carbonate plus 100 grams of water, we get a 0.280. So that is our mass fraction for sodium carbonate at feed. Next is we have to calculate the mass fraction of water in the feed. So given the sodium carbonate, we have 0.280. So we have to minus 1 from 0.280. So we get the answer of 0.720, and that is our mass fraction for water. The next thing we have to do is to calculate the mass fraction of mother liquor, or in the product. So we have to set a basis of 1 gram per mole of sodium carbonate decahydrate. So sodium carbonate we have given of 1 mole, and the molar mass is 106 grams per mole. For water, we have 10 mole, and given the molar mass of 18 grams per mole. So to get this 0.371 and 0.629, we have to calculate the mass fraction. So the same procedure is used in calculating the mass fraction of sodium carbonate and water in the feed. So we get 0.371 for mass fraction of sodium carbonate at mother liquor and 0.629 mass fraction of water in mother liquor. Since we already solved the mass fractions of sodium carbonate and water in feed and product, we have to rewrite the block diagram and write the correct components. So we have in the feed 10,000 kilograms, 0.280 sodium carbonate, 0.720 water, and 30 degrees Celsius solubility of 0.388. And at the crystals, we have still 3,000 kilograms of sodium carbonate, and we have 0.371 mass fraction and 0.629. So in this case, we should solve for the components in the mother liquor or in the product. To solve for the components in the mother liquor, we should do the overall mass balance. So we have feed equals to crystal plus product or mother liquor. So in the block diagram, we have seen that the mass that is coming inside the crystallizer is 10,000. So therefore the feed is equals to 10,000 equals the crystals of 3,000 and mother liquor or the product is unknown. So solving the product, we have get 7,000 kilograms. So after solving the OMB, we do the sodium carbonate balance. So we have the feed times the mass fraction in the feed equals the crystal plus the mass fraction in the crystal plus product times the mass fraction in the product. So since we are looking for the mass fraction in the product, we should plug in the values given in the block diagram. So therefore we get the answer of 0.241. So we already solved for the mass fraction of Na2CO3 in the product. So now we could also calculate the mass of sodium carbonate and we have 1,687 kilograms. So we are done in part A and now we proceed to the second question. So if the feed is cooled to 10 degrees Celsius, where 3,000 kilograms of sodium carbonate decahydrate is removed, the average heat capacity of the feed solution can be assumed as 3.12 kilojoules per kilogram Kelvin. The heat of solution at 25 degrees Celsius is negative 10.25 times 10 to the power of 3 kilojoules per kilogram mole. So determine the total heat absorbed and no evaporation. To solve for the heat, we must use the formula H is equals to m Cp delta T, where m stands for mass, Cp for heat capacity, and delta T for change in temperature. For H1, we plug in the values in the feed, so we have 10,000 kilograms given the specific heat of 3.12 and the temperature of 30 minus 10 degrees Celsius. So solving H1, we have 624,000 kilojoules. The same procedure is done in solving for H2. So we are given the heat of solution with negative 10.25 times 10 to the power of 3 kilojoules per kilogram mole sodium carbonate decahydrate. So to solve for H2, we multiply the heat of solution to 1 kilomole over 280 kilogram sodium carbonate decahydrate. Now we arrive at the answer of negative 35.81 kilojoules per kilogram crystals. And now we multiply it by 3,000 kilogram of crystals, so we get negative 107.442.35 kilojoules. So to solve for Q, at equilibrium, the heat of crystallization is equal to the negative of heat of solute. We have Q is equals to HA plus HV minus HB, where HV is equals to 0, since we are only solving for the total heat absorbed. So we have the values of negative 107,442.35 from H2. We deduct it with the H1. So we get the final answer of Q equals to negative 731,442,000.35 kilojoules.
Hello there! Now, we'll be dealing with a sample problem of evaporation involving heat and mass transfer. Problem 1. The problem states that a feed of 4,535 kg per hour of a 2.08% salt solution at 311 Kelvin enters continuously A single effect evaporator is being concentrated to 3.0%. The evaporation is at atmospheric pressure, and the area of the evaporator is 69.7 square meters. Saturated steam at 383.2 Kelvin is supplied for heating. Since the solution is dilute, it can be assumed to have the same boiling point as water. The heat capacity of the feed can be taken as Cp equals 4.10 kilojoules per kilogram Kelvin. Calculate the amounts of vapor and liquid and the overall heat transfer coefficient U. Now, evaporation is a unit operation, and in dealing with unit operation problems, we have to consider doing a free body diagram, or simply the FBD. So, based on this problem, our FBD would possibly look like this. Now, as you can see, we have two inputs, two arrows showing the inputs. We also have two arrows for the outputs. Now, first, let's consider the first arrow, which shows the feed of 4,535 kg per hour, the percentage weight given of 2.0%, and is in decimal, which is 0.02, and its temperature at 311 Kelvin. The next one is the saturated steam input, in which the only given is its temperature at 383.2 Kelvin. Moreover, on the output side, we have the temperature of the vapor at 373.15 Kelvin, while the vapor, the amount of vapor and its enthalpy is still unknown. Lastly, the liquid product denoted as L is still unknown, and we have already the given of percentage weight of solute, which is 3% or 0.03. And lastly, the temperature at the liquid product is at 373.15 Kelvin. And lastly, the given of this problem is that the area of our evaporator is 69.7 square meters. Okay, so now that we're done with our free body diagram, let's now proceed with the assumptions. Now, for this given problem, we can assume that number one, system is in steady state, and we can also assume that there is no heat lost by radiation or convection. Next thing we will do is to list down what we are going to find in this problem, or what are the required quantities. So first, we are required to find the amounts of vapor V and liquid product L, and also the overall heat transfer coefficient denoted as U. From our given data, we can solve first the amounts of liquid and vapor. So going back to our free body diagram, as you can see here, by doing a material balance, we can solve for the value or the amount of liquid product denoted as L. So by doing a solute balance, we have here the feed multiplied by its percent concentration, and it is equal to the product L multiplied by its solute concentration as well. Plugging in the values, the only unknown here is the L, the liquid product, and by that we can already solve for its value, wherein L is equal to 3,023.3333 kilograms. Now, from that amount of L, we can do an overall balance to get the value of V. So F is equals to V plus L. Remember, input is equal to output. So 4,535, which is the F, is equal to V plus 3023.3333. We now have the value of V, 1,511.6667 kilograms. So now we have the amounts of L, the liquid product, and V as a vapor. So we now have the first required quantities. Now let's proceed in solving the overall heat transfer coefficient U. So first things first, we have to take note of the different values that we'll be needing in solving the overall heat transfer coefficient. So one would be its enthalpy. So we have to look for a table that has the properties of saturated steam and water. So we have here a table. So this table here is from the book of John Coplis. So you can look for it, or it also has, we can also find it in Paris, of course. So from this table, we can get the enthalpy of water both in liquid and in saturated vapor. So from here, since we are dealing with water at its boiling point, which is 100 degrees Celsius, and from this table, the given here, the unit is in degree Fahrenheit. So we'll be converting 100 degrees Celsius to Fahrenheit. And 100 degrees Celsius is equivalent to 212 Fahrenheit. So here we go. So from here, we have to look for its enthalpy. So we have here the value 180.16, the enthalpy of water in liquid form, and in saturated vapor it is 1150.5. But since the unit here is in BTU per pound mass, we'll be needing a conversion factor. So we have here 1 BTU per pound mass, or 1 British thermal unit per pound mass, is equivalent to 2.326 kilojoules per kilogram. So we'll be needing this to convert our values in kilojoules per kilogram. So the enthalpy of liquid would be 419.05 kilojoules per kilogram, while the enthalpy of saturated vapor will be 2676.06 kilojoules per kilogram. After we take down of the quantities and values that we'll be needing this computation, we now have to do an energy balance for us to come up with the final equation that we'll be needing to compute for the overall heat transfer coefficient nu. So in doing so, we just have to multiply the amounts of feed, the steam, the liquid, and the vapor to its corresponding enthalpies. So from here, we can come up with our final equation, which is this. So the feed multiplied by its heat capacity multiplied by the quantity of the temperature in feed minus the temperature of liquid plus the heat transfer coefficient nu multiplied by the area times the quantity of the temperature of steam minus the temperature of vapor is equal to the vapor, the amount of vapor, times the quantity, the enthalpy of saturated vapor minus the enthalpy of liquid. So from this, substituting the values gives us this equation. So as you can see, only the overall heat transfer coefficient U is the unknown, and from that we can calculate for the value. So U is equal to 6552.99 kilojoules per hour square meters Kelvin. And with this, we can convert kilojoules to joules and hour to seconds. Resulting units would be joules per second square meters Kelvin. And take note that 1 joule per second is equivalent to 1 watts. Therefore, our final overall heat transfer coefficient U is equivalent to 1820.3 watts per square meters times Kelvin.